This is a tutorial of ALISA, the architecture-led incremental systems assurance capability in OSATE. We will proceed by first giving a background on ALISA and an overview of its capabilities, introduce the ALISA notations, and then go into details about verifiable system requirements, developing verification plans for those, defining categories and filters to be able to see subset views of your system assurance plans. And then we go into details of how to configure assurance cases and execute those continually throughout the life cycle. We then close out by talking about reusable global requirements, as well as how to provide a link to stakeholder goals and tie them to system requirements that become verifiable. For background, we are familiar with the issue of critical systems and the challenges we have in assuring that they work correctly. Studies have shown, and you have seen those numbers before, that 70% of the system problems are introduced during requirements and architecture design, and 80% are not discovered until after post-unit test. As a result, we have had very high system costs, and the ratio of software as the total system development cost has changed from 45% to 70% today, and going higher in the future. As I mentioned, today we are already spending 50% of the total system development cost on post-unit test software rework. And clearly, recertification cost is not proportional to system changes, and as a result of that, we are often not pushing out system changes into an operational system because of recertification, although they fix issues in the operation. As a result of that, we have now software as a major system hazard, and system safety assessment processes that are currently in place are very labor intensive, with people developing spreadsheet-like information as they do, for example, in FMEA type of processes. In a study that was done for the AMERDEC Aviation Engineering Directorate, we looked at a strategy for improving the situation. And the idea with assurance is to have sufficient evidence that the system implementation meets system requirements, which means, first of all, the system requirements have to be good and reasonable, because that's what you verify against. And secondly, we want to do verification and do that throughout the process so we can catch problems close to the time they're introduced. That strategy has 4 pillars. 2 of them focus around the use of AADL, what we call architecture-centric virtual integration, or ACVIP, in the context of the Army JMR. The 2 main pillars are the use of architectural modeling and using that to do virtual system integration and analysis of those systems. That's the second pillar, through static analysis as well as simulation and compositional verification, to deal with not just functional properties but non-functional properties of the system. That's complemented with 2 more pillars. That's then the major contribution of the ALISA part, namely having specified requirements that are verifiable and deal with not just functional but non-functional properties of the system, layout verification plans, and then on the back end, as we throughout the life cycle continue to execute the verification activities in those plans. Verification plans is what traditionally was called test plans, but test plans tend to focus primarily on just code testing. We are talking about verifying systems throughout the life cycle. So on the back end, as we maintain a record of those verifications, we can then basically build up an assurance case type of record of our system. Why are requirements important? When we have textual requirements, there are some statistics that show that often the requirements are incomplete, missing, incorrect, ambiguous, and inconsistent, and they So there's low-hanging fruit in improving the requirement situation. Another interesting study is one by Rolls-Royce in the UK, where they recognized that requirement changes or system design changes were requested by the development team more than by the end customer, and that was for an engine that has already been in production and was being tailored to particular customers. What they then were able to do is get the engineers to comment on what they think the areas are in which they need to change the requirements, and as a result of that, having a record of that just by interviewing engineers and then making use of that information, they were able to reduce requirement changes by 50%. And we are building on that by providing ways of recording volatility and other forms of requirement uncertainty and weighting of those in order to drive development. In terms of requirement coverage, making sure that we have requirements on all parts of the system that need to be verified. First, we take a look at a definition of what a system is. This is a definition from the French System Engineering Society, which says a system takes input, produces output through behavior and state, utilizing resources and living under some form of control or constraint that they need to operate on. What that means now is we have to have requirements on all those elements. On the inputs, those are often then referred to as assumptions. On the outputs, sometimes they're referred to as guarantees. The utilization of resources, like the assumptions we are making about availability of networks and compute resources and so on. The second class of requirements falls into dealing with the different quality attributes, and there we can make use of utility trees to drive those requirements down to concrete requirements that become verifiable. So saying that the system needs to be secure is not sufficient. We need to elaborate that into what kind of security are we talking about, and similarly on performance, we need to drive it down to very specific numbers. The third area then deals with exceptional conditions in the system, and there we can utilize the taxonomy that comes with the ERA model version 2 to identify exceptional conditions or fault classifications that then get propagated to other parts of the system. And if we apply those systematically to our inputs and outputs and system state, we then can characterize the fault behavior of the system. And at the bottom right, that picture looks very much like a picture that Nancy Leveson has as part of her STPA safety analysis process. The third major element of ALISA is incremental assurance, and there are 3 dimensions of that. One dimension has to do with the life cycle. We have our double V, where we are building the system, not just on the left part, but we continue to specify things like integration, kind of configuration and type of information. On the other hand, what used to be the right-hand side of the V for testing and verification, we now extend that into the left side and start verifying early in the process, which then leads us to our double V, and we incrementally, as we evolve our system design, continue to reevaluate the system. The second piece of it is that in many cases you're focused on certain aspects of the system that you want to improve. For example, the interplay between timing and safety, or focus on a particular subsystem that seems to have lots of requirement changes or problems. So we want to be able to have support to focus on high payoff areas for analysis, and you will see that in the filtering process that we support based on categorization of requirements and verification activities. The third element is that we can do the whole thing incrementally through compositional type of verification, and use of partitioning in your system can then limit the amount of re-verification that needs to be performed, and again, we utilize techniques for that. If we apply these techniques, you are the benefits. We have improved requirement quality through coverage and managed uncertainty. We have improved evidence quality through compositional analytical verification, and we can measurably reduce the certification related to rework costs through integration and verification automation. And finally, we have a historical record of how well we are doing, not just in the end when we deliver the assurance case result where everything is expected to be green or positive, but throughout the life cycle we get feedback from the ALISA system as to what areas are satisfying their verification plans and which ones are failing in certain verification activities. A short summary of some pointers to information about ALISA. There is the online documentation built in OSATE with a reference to accessing it over the web. There are a couple of papers. There are some technical reports, one around the RegSpec notation, and there's actually 3 reports around the JMR shadow project. And we have a link to a GitHub area of OSATE in which we have ALISA examples.